now.
Thanks, Jim. Hi, everybody. Welcome to a new age, or at least a new time. It's daylight savings time here in the United States, which has caused us a little bit of confusion here on the broadcast, but we figured it out thanks to our crack team. Got it together. I'm so glad you were able to come back today. We've got a good program for you today. We're gonna get back to the history of astronomy, one of the most important things that like 100 years ago, they didn't know that Andromeda galaxy was a galaxy. It was called the Andromeda Nebula, and that was pretty cool. Okay,
So right
hey,
about the time you were graduating college, right?
we've been having some problem with the staff. Anyway, Rod's going to be here today, and he's going to tell us how they solved the Great Debate. Okay, he's going to tell us a little bit about that. Yizhu Zhang is going to come in next week and tell us about sharing on a remote setup and how he worked out a crew like that. And then the next week, we've got some people coming in. I'm going to let Rory tell you about what's happening the next week. Rory, you want to go ahead? You want me to stop sharing so you can get in here, or?
No, it's okay. I can just talk from
Okay.
here. Today was the last day to submit photos for the TAC workshop. In 2 weeks, I'm going to be doing the TAC workshop with Jason, Dane, John Richards, Matteo, and Brandon Nance. So I had 4 people submit so far. They're images of Terry's Tarantula Nebula, getting a lot of interesting shots as there was a lot of different color channels to work with on there. So excited for that show, and that's all I have for today. Thank you.
Okay. Now, that data will stay there, and you can, this is the current workshop, and you can get the zip files here, stuff like that. I don't think we'll be able to getting you into the show anymore, but go ahead and submit it anyway. And you can also go back and get some of the other workshops that we've done through time. We've found a place on the web out there someplace, and all the data is still there, and you can go back and you can go find the shows where we did the workshops, and you can see how they work. We have also got TAIC shots coming up, the Astro Imaging Channel user shots. Oh, hey, this is Rod's picture of Saturn. Rod is our presenter tonight, and he happened to be one of the people who submitted something for the TAIC shots. You've got until April 3rd to turn these in, and we do need some people to turn them in. Last week, we changed the rules. Usually our rules is it's got to be this apparition, this time around the sun. This time, we're going to say anything because we just haven't gotten a lot of entries in this. So please get them in here for us, okay? You can also send in a movie if you like. But anyway, you just click there to submit, and you've got till April 3rd to do it, and we'll put it together, and we'll make a little movie out of it so that you can see your wonderful shots and tell your grandkids how you were on YouTube and stuff like that. I don't know. It's fairly exciting to do. Okay. We've got a couple of blanks coming up. The NEAC show, we weren't going to have a show, but we are in fact going to have a show, but I haven't figured out quite what's going to fit in there. And then we've got a whole lot. But then up until Sunday, May 29th, and on Sunday, May 29th, we got a problem. We don't have any more shows. We don't have any more people scheduled. So we need you to get together and volunteer. And the way you volunteer, it's pretty easy, really. You just hit the contact button and you tell us what your name is. You give us your email, of course, and then tell us what you'd like to talk about. We are looking for people. You should be good. You should be able to complete sentences and stuff like that. Most people like to use a PowerPoint. We all pretty much know how to do that. And I figure if you're smart enough to do astroimaging, you're smart enough to share what you do in astroimaging with other people. So please, if you've got something that you think's kind of cool, even if it's pretty basic, there's a lot of people that are still in the basic stuff and they still need to learn that stuff. If you got some helpful hints, or you found a technique that works good for you, go ahead and tell us about it. We've got a guy tonight, Rod Pommier, who decided that he was going to tell us about the Great Debate. So if I could get back to Rod, time to turn it over to you. Can you take over from here?
I will take over, Alex. Thank you. And I'll take a verbal confirmation that I'm showing up on YouTube, please.
Astrophotography to calculate the distance to M31.
Excellent. Well, good evening, everyone. My name is Rod Pommier, and I'm in Portland, Oregon, and it's my pleasure to talk to you tonight about astrophotography, both professional and amateur, to calculate the distance to M31. So I'll begin with the customary about me slides, both professional and my astronomy life. So as a profession, I am a surgical oncologist, which means I'm a cancer surgeon. I operate almost exclusively on people with cancer to remove their tumors as a fundamental part of their cancer treatment. I'm what you call an academic surgeon, so I practice at the Oregon Health and Science University here in Portland, where I'm actually a professor of surgery, which means I teach surgery chiefly to general surgery residents training to become surgeons, but also to medical students who are training to become physicians. And also as a professor, I conduct and publish research on cancer and the outcomes of my operation. But what's much more interesting is my astronomy life. I started as an amateur astronomer at age 12 when I saved up and bought my first refractor. I started astrophotography way back in 1986. Those were the heady days of film and hand guiding, not auto guiding, hand guiding your images out in the cold all night to get a single exposure on gas hypersensitized film that was baked in an oven with hydrogen and nitrogen and cooled out in the field with dry ice. So we've come a long way into digital astrophotography. I'm happy to report that I've had a lot of images published in both Sky and Telescope and Astronomy magazine. Other images have been used in other media, like one's been used by Neil deGrasse Tyson in a show, and on how the universe works on the Discovery Channel. Perhaps the biggest compliment I get is when a professional astronomer asks to use one of my images as an illustration in one of their publications about research or a press release about their research. For 31 years, I've been writing and publish articles in Sky and Telescope and Astronomy, chiefly about observing, but some about astrophotography techniques. And typically, I'll illustrate those entirely with my own astrophotographs. And speaking of which, this topic tonight is going to be my next article in Astronomy magazine. It's due to come out in the August 2022 issue. So I'd like to give a big thanks to my longtime pal, Dave Eicher, the editor of Astronomy magazine, for allowing me to present this here tonight to you before it appears in print, because technically the magazine had first rights to this material. So if I ask us all to think back to when we first got started in astrophotography, I think many of us would recall that one of the very first objects we wanted to capture was Messier 31 in Andromeda, and with good reason. It's big, it's bright, you don't need a particularly sophisticated system to get a decent image of it. Perhaps the most compelling reason you wanted that image was because once you had it, you could show it to people and say, this is an image I took of another galaxy. It lies far outside our own Milky Way at a staggering distance of 2,537,000 light years. And people would get the importance of that. The concept of other galaxies is now firmly entrenched in our culture. It's in our science and even our science fiction. After all, the Star Wars saga is held a long time ago in a galaxy far, far away. But we haven't always known that M31 is another galaxy. In fact, as Alex mentioned, we've known it for less than a century. Prior to that, M31 and all of the other great galaxies in the sky, like M81, M51, M101, and M33, just to name a few, were not referred to as galaxies at all. Rather, they were referred to as spiral nebulae because of the shapes that I just showed you. And nobody knew what they were or their distances. In fact, the true nature of the spiral nebulae was a hotly debated issue. On April 26, 1920, astronomer Harlow Shapley of the Mount Wilson Observatory debated Heber Curtis of the Lick Observatory on the nature of the spiral nebulae and the scale of the universe in front of the National Academy of Sciences here in Baird Hall at the Smithsonian Institute. This event is now referred to as the Great Debate. Now, Shapley had recently measured the diameter of the Milky Way and found it to be on the order of hundreds of thousands of light years, far bigger than astronomers had previously imagined. Therefore, he believed the Milky Way was the entire universe and nothing lay outside of it. Therefore, in his view, the spiral nebulae had to be smaller structures lying inside of it. Perhaps they were swirling stellar nurseries giving birth to star clusters, or other solar systems caught in the act of their formation, with the central bulge condensing into a star and the spiral arms condensing into orbiting planets. On the other hand, Curtis argued that they were other galaxies, just like the Milky Way, and therefore were enormous structures lying at tremendous distances. Now, while Curtis is said to have been the better speaker, the debate had no clear winner. Then, beginning in the fall of 1923, Edwin Hubble solved the mystery of the spiral nebulae. He started taking images of M31 using the 100-inch Hooker telescope atop Mount Wilson, then the largest telescope in the world. And he took images on photographic glass plates, and on one of those plates, he found a variable star. And here's a montage that shows the original negative, which here is enlarged and turned into a positive, with a zoomed in view of the variable star that he found, that he marked with tick marks and labeled. And you can see it forms a nice little isosceles triangle with what turned out to be two foreground Milky Way stars. And then Hubble photographed this variable star on every successive clear night he could. And he used those images to prove beyond a shadow of a doubt that M31 was another galaxy. But the implications went far beyond just M31 being another galaxy. This also implied that all of the prominent spiral nebulae in the Messier catalog were other galaxies, and all of the prominent spiral nebulae in the NGC catalog were other galaxies. But the implications went still farther. Because if you look at an image of any prominent Messier or NGC galaxy, in the background, you'll see numerous other smaller spirals. These smaller spirals are present in absolutely staggering numbers. Hubble had already done a survey of the sky and estimated that the sky contained at least 1 million of them. They were present in a bewildering variety of sizes, shapes, and orientations. And the final implication of Hubble's discovery was that if these smaller spirals were other galaxies in their own right, only still farther away, well, then the scale of the universe was unbelievably enormous. So this is one of the most epic discoveries in astronomy. And it's important for us as astroimagers to realize this feat was accomplished using our hobby of astrophotography. This is arguably the most important astrophotograph yet taken. And this faint star on that image, which has since been dubbed M31V1 for the first variable found in M31, is quite literally the star that changed the universe. Now, as an avid astrophotographer and someone looking for interesting targets, I really wanted to take my own image of the star that changed the universe. But could I? Unlike Hubble, I don't have access to a 90-foot dome that houses a 100-inch telescope. Rather, I have access to my own 10-foot dome, which houses a 14-inch telescope, and that is magnitudes smaller. On the other hand, I do have a cooled CCD camera, which is magnitudes more sensitive to light than Hubble's slow photographic glass plates. So this raised a very interesting question for me. Could a 14-inch telescope combined with a cooled CCD camera possibly match a 100-inch telescope equipped only with slow photographic glass plates for this very faint target? So I decided to do some research and see if other amateurs had successfully imaged M31V1. And I very quickly found this paper written by 11 members of the American Association of Variable Star Observers. Back in the latter half of 2010, they were tasked by the Space Telescope Science Institute to image M31V1 and try to derive a modern ephemeris of when it reaches maximum brightness. So the Space Telescope Science Institute would know when best to point the Hubble Space Telescope at it and obtain images as part of this public outreach program. And as you can see, they were successful. They predicted it would reach maximum brightness on January 26, 2011. And in reading their paper, they described M31V1 as a difficult but achievable target for team members equipped with modern CCD cameras and larger telescopes. Unfortunately for me, how large was not specified. Still, their successful report convinced me that I should at least attempt to try to image M31 myself. But then a much bigger question washed over me. If I could successfully image M31V1, could I collect a series of images and use my images to do what Hubble had done and prove that M31 is so far away it has to be another galaxy myself using my own data? That would allow me to relive one of the most epic discoveries in the history of astronomy, and that would be a fantastic astrophotography project. And we're currently approaching the centennial of Hubble's work, so what better time to emulate his project? But I also quickly realized that if I was going to do this, I wouldn't need to just reproduce what Hubble had done as an astrophotographer and take a bunch of images of M31. Rather, I would need to understand how Hubble had used those images to prove M31 is so far away, it has to be another galaxy, so that I could do the same with my images. And that proved to be a story that's very rich in the history of astrophotography. And I'll explain that to you now so that you can understand the project I undertook. So how did Hubble do this? Well, he did it by finding within M31 an object known as a standard candle. Standard candles are objects of known brightness or luminosity. This concept of standard candles is actually very familiar to us in everyday life. If you know how bright an object truly is, like the streetlight you're standing under, you can compare that to similar instances of it at a distance, such as the streetlights down the road. And then by comparing the difference in brightness, you can work out how far away those objects really are. The standard candle that Hubble found within M31 was a Cepheid variable star. These are rare, pulsating variable stars that vary in brightness over times ranging from 1 to 120 days. They're named for the prototype star Delta Cephei, which was discovered to be a variable by John Goodrich, a deaf Yorkshire amateur astronomer in 1784. And to the right is his report to Neville Maskelyne, the Astronomer Royal, which was read before the Royal Astronomical Society on November 24th, 1785, and then published here in their annals. Cepheids all exhibit a characteristic pattern if you graph their magnitude versus time, called a light curve. That curve is characterized by a rapid increase in brightness followed by a much slower decline. And this pattern repeats at very regular intervals, as regular as clockwork, called the period, and that's typically measured between maxima. They always return to the same maximum brightness and the same minimum brightness, and the difference between those magnitudes is known as the amplitude. This characteristic sawtooth pattern makes Cepheids very easy to identify among all the types of variable stars visible in the sky. Henrietta Swan Leavitt, who was also deaf, noticed that there was a very strong relationship between a Cepheid's period and its maximum brightness. She was one of the many women hired by Edward Charles Pickering in the late 19th and early 20th century to work as human computers at the Harvard College Observatory. She was chiefly charged with measuring the magnitudes of stars on the observatory's glass photographic plates. But a special aspect of her work was to search for new variable stars if she saw something vary in brightness between two photographs taken of the same region of sky on different nights. In the early part of the 20th century, she was examining plates of the Large and Small Magellanic Cloud taken at the university's satellite observatory in Arequipa, Peru. And on these plates, she found a record 1,777 new variable stars, 47 of which exhibited the characteristic pattern of Cepheids. Now, her absolutely brilliant observation was the longer the period, the brighter the apparent magnitude, which is denoted by a lowercase m, was at maximum. Now, I think we all know that how bright a star appears from Earth is no indication of how bright it really is. It might be a dim star close to Earth, it might be a brilliant star very far away. But she correctly reasoned that because all of these Cepheids were contained in the same deep sky object, namely a Magellanic Cloud, they must all lie at nearly the same distance from Earth, much as all of her relatives scattered across the state of Wisconsin lived roughly the same distance from her in Cambridge, Massachusetts. That meant their apparent magnitudes were accurate representations of their true luminosities. And this in turn implied there had to be a relationship between their periods and their true luminosities. So in 1912, based solely on 25 Cepheids in the Small Magellanica Cloud, she published this landmark graph showing a strong linear relationship between the logarithm of the period of Cepheids in days and their apparent magnitudes. The upper squiggly line is a connect the dots of the 25 Cepheids maxima. The bottom squiggly line is a connect the dots of their minima. And despite this variability, the best fit lines through both of those curves were absolutely parallel. So because of this variability, she proposed that the relationship was best expressed as one between the logarithm of the period in days and their average apparent magnitude. And that's a convention that is still used today. This is now known as the period luminosity relationship, or Leavitt law, and it is one of the most important principles in astrophysics. Danish astronomer Einar Hertzsprung realized the tremendous significance of Leavitt's discovery. He knew that if the distance to any Cepheids could be determined, well, then you could work out how bright they really were. And then Leavitt's graph could be calibrated with their absolute magnitudes, which is denoted by a capital M. That would enable their use as standard candles. And from then on, the distance to any Cepheid anywhere could be determined only using two pieces of data: its period and its apparent magnitude. You would use the logarithm of the period to figure out how bright the star really was, or its absolute magnitude, capital M, on a period luminosity graph that had been calibrated. And then you could compare its absolute magnitude to its apparent magnitude from here on Earth and determine how far away it was. Now, the most accurate way to determine the distance to a star is with trigonometric parallax, where you measure the apparent shift of a foreground star against distant background stars by measuring its position 6 months apart when the Earth has traveled 186 million miles in the diameter of its orbit. This works pretty well out to a distance of 45 light years, maybe 100 if you really push it. The problem was no Cepheids lay within that range. So instead, Hertzsprung used the much more complicated and far less accurate method of statistical parallax to estimate the distance to 13 Cepheids, including Delta Cephei. And then he worked backwards. He used the apparent magnitudes and the distance he got to calculate their absolute magnitudes, or capital M. And with that, he went about calibrating Leavitt's period luminosity relationship. So in essence, he took these apparent magnitudes on Leavitt's graph and replaced them with their absolute magnitudes, and then he solved the equation for this line. And he came up with the equation absolute magnitude is equal to minus 0.6 minus 2.1 times the log of the period in days, which is basically a form of y equals mx plus b. Now, Hertzsprung's estimates of the distance to Cepheids were crude at best, which means this equation, although it was the first calibration of the PL relationship, was very far off the mark. The first thing he did with it was to calculate the distance to Leavitt's Cepheids in the Small Magellanica Cloud, and he came up with a distance of 30,000 light years, and we now know that the distance is 200,000 light years, so he was off by more than a factor of 6. Harlow Shapley did not like Hertzsprung's calibration, so he revised it. He threw out two of the Cepheids that Hertzsprung used, and then he included stars that he found in globular clusters, which he believed were Cepheids, and some were and others were not. So his calibration was also off the mark. But he used the distance to the globular clusters by calculating from Cepheids, and he estimated the diameter of the Milky Way to be 300,000 light years. And of course, we now know it's 100,000 light years. So his calibration was better, but still off by a factor of 3. However, he did use the distance to globular clusters to show that we are not at the center of the Milky Way, as had been previously assumed, but well towards the outskirts of the Milky Way. And that gave us our biggest demotion of position in the universe since Copernicus put the sun at the center of the solar system. However, a much bigger demotion was just around the corner. Beginning in the fall of 1923, Hubble used the 100-inch Hooker telescope, the largest in the world, to begin photographing M31. And on the night of October 5th and 6th, he found on plate H335H. He labeled the first H for the Hooker telescope, and the second H was for Hubble. But on this plate, he found 3 new stars that he did not think were present before. And so he took out his customary black marking pen, marked the positions of the stars with tick marks, and labeled them with N's for novae. But before he published this finding, he wanted to verify that it was real. So he took the plates down to the university's observatory's main offices in Pasadena and compared them to archival plates going as far back as 1909. When he did that, he confirmed that these lower 2 stars were indeed brand new, but the remaining star at the top was not. It was present on other plates going back as far as 1909, but it varied in brightness. So Hubble knew it couldn't be a nova and had to be a variable star. So at some point, he took out a red marking pen, very different from his usual custom, crossed out the letter N with a big red X and wrote capital V, capital A, capital R, exclamation point for variable. Hubble knew that if this was a Cepheid, then he had struck astronomical gold. If he could measure the period and the average magnitude of this Cepheid, he could calculate the distance to M31 and solve the mystery of the spiral nebulae. So beginning in January of 1924, Hubble photographed M31V1 every successive clear night that he could. And after he analyzed all of his plates, he plotted the magnitude versus time on this sheet of graph paper, and then he drew a best fit curve through it. And the first question he asked is whether or not this was characteristic of a Cepheid. And he convinced himself it was. You can see over here on the right that he caught the very rapid brightening of the Cepheid on 3 successive nights of February 5, 6, and 7, 1924. So then he measured the period, and he found it to be 31.415 days, and he estimated the median magnitude of the star to be 18.5. Using the period, he estimated the absolute magnitude, capital M, to be minus 5.0 from some calibrated period luminosity relationship. And of course, he then knew that for a star of absolute magnitude minus 5.0 to have an apparent magnitude of 18.5, it had to be very far away. And he calculated that distance to be 220,000 parsecs, which is about 770,000 light years. So that was well outside even Shapley's overinflated Milky Way, proving it had to be another galaxy. Now, Hubble was previously a lawyer, so he was very cautious before he published this, and he gathered a lot more data before he finally published his estimate of the distance to M31 in the Astrophysical Journal in 1929. And you can see here that he used Shapley's calibration of the period luminosity relationship and came up with his final estimate of 900,000 light years. The same errors that caused Shapley to overestimate the diameter of the Milky Way caused Hubble to underestimate the distance to M31. But Shapley's calibration was considered the best available at the time. So that's a whirlwind tour through the history of how Hubble did it. Do we have any questions at this time about how we actually determined the distance to M31 before I go on to my actual project?
I think everyone over on BlueTube is kind of raptured, just waiting to get to your actual data to see how you did that. Actually, I say that it's maybe I'm the only one that's in rapture waiting for your data.
All right. Well, hold on, Eric. We'll keep going forward. So from the foregoing presentation, it should be obvious that if I was going to reproduce Hubble's work, I was going to have to do several things. I would need to image M31V1 on as many successive clear nights as possible. Then I would need to measure M31V1's nightly magnitude, and then I would use that to produce my own light curve from which I could derive M31V1's period and its average apparent magnitude, or little m. Then I would use the period to derive M31V1's absolute magnitude, or capital M, from calibrated period luminosity relationships. And then I could compare the apparent and absolute magnitudes to calculate a distance to M31. Now, Hubble measured the magnitude of the stars on his photographic glass plates by measuring the diameter of the spots through a microscope. These days, we measure magnitudes on digital images using photometry software. Photometry software will measure the counts on a target star that you want to know the magnitude of and compare it to the counts of another star on the same image whose magnitude is known. But you have to calibrate the software. And so fortunately, many of the programs we use like MaximDL and PixInsight contain photometry tools for this very purpose. Well, let's see how this works. So let's suppose I wanted to know the magnitude of this target star, which by the way is not a variable, near M66 in this image. Well, first I need a comparison star. So I picked this star and I looked it up on the SkyX, verified that it is not a variable, and the SkyX told me it has a magnitude of 11.37. So to calibrate the software, I type the magnitude of that star in this window, hit extract from image, and then go click on that comparison star, and that calibrates the software. After that, I can move the bullseye to my target star, and up here I get a reading of its magnitude, which turns out to be 10.957. Now I would round that up to 10.96 because I only have 2 decimal places in my comparison star. So how does the software work? Well, I looked up that star, that's my target star on the SkyX, and it indeed tells me that the magnitude is 10.96. So the software works very well. So how do I get comparison stars for M31V1? Well, if you go to the AAVSO website, they have a function called the star plotter. You can enter the coordinates of any target star you want in a field of view, and it will print a star chart that matches your image. And if there are any known comparison stars in that field, it will plot them on the chart. But it leaves out the decimal places because those might be confused as faint stars. So for example, this star here is magnitude 15.5. So I was very happy that as part of the 2010 project, the 11 members of that project had plotted numerous comparison stars within 15 arc minutes of M31V1 using magnitudes from the United States Naval Observatory database. So going on to plan the project, I decided I would use a clear filter to capture as many photons as possible. There's no reason to use a color filter for this and exclude photons. Now the native focal ratio of my telescope is f11, which is quite slow, and I might not get enough photons captured in a single night during the summer. So I decided to insert my Starizona large format reducer corrector into my imaging train, and with f7.5, I would reduce my nightly exposure times greatly. I knew from previous variable star work that you get the best magnitude readings if you bin your images one by one, but it's also critical to have very good flat field frames to even out the background. And for a very faint target like this, it's really important that I have very good flat fields. So I committed to take new flat fields every night. Now, Hubble didn't know how many nights he would have to image M31V1 to catch its period. I wanted to pretend that I didn't know either, but of course in the back of my mind I knew it was 31 days and probably longer. I wouldn't know where M31V1 would be in its cycle when I started imaging, so I would likely have to track it until it peaked in brightness, then for another month after that until it peaked again, and probably still longer to make sure it was fading yet another time. And so if I was going to be imaging more than a month, it was certain I would be imaging when there was a full moon in the sky. And as celestial mechanics would have it, the full moons were going to be very near M31 during the upcoming months. So I became quite concerned that I would have bright moonlight flooding down my optical tube and washing out my CCD chip, and I might lose M31V1, particularly if the full moon coincided with the fainter portions of the cycle. But there was nothing to do but forge on ahead. So the next thing I had to do was figure out how I would frame M31V1. And so even with the f7.5 focal reducer, this is still high resolution astrophotography, and M31 will not fit in the entire frame of view of my CCD camera. Another problem you have with high resolution astrophotography is that there is virtually never an adequate guide star in your guide chip. So you also have to figure out how you're going to rotate the camera to acquire a guide star so you can track your images. So where is M31V1 within M31? Well, its coordinates are 0 hours, 41 minutes, 27.3 seconds, declination plus 41 degrees, 10 minutes, 10 seconds. So using the same image planning software, I shifted to those coordinates, and then I found that if I would rotate my camera to a position angle of 135 degrees, that would put M31V1 at the center of my chip, and at the same time, I would acquire this lovely magnitude 7.2 star SAO 3245 in the center of my guide chip so I could track my images. And with that, I was ready to start imaging. So the weather is best here in Portland, Oregon in the summer and early fall, and that's when M31 is pretty high in the sky. So I started in early August around 1 a.m. when M31 is finally at least 45 degrees above the horizon, so I wouldn't have problems with atmospheric extinction. And on the first night, I captured about 2 hours of data before the typical Portland clouds came rolling in and put an end to that night observing. But the next day, I calibrated those frames and stacked them. And here is my very first frame on my very first night. And of course, I was extremely eager to look at the center of this chip and see if I had captured M31V1 or not. So zooming in on that, indeed, there was M31V1 as a faint dot making a little isosceles triangle with those two foreground Milky Way stars. And I got to tell you, I stopped and stared at this image for the longest time. I've been an astrophotographer for 35 years, and I have inspected countless stars on my images. And no star I've ever imaged has been as inconspicuous and seemingly insignificant as this faint little dot. Yet nothing I've ever imaged has been more important to cosmology and our understanding of our place in the universe than this faint little dot. So finally capturing it on an image I took myself really took my breath away. And then I was hooked. I mean, I went out every night, no matter what, to image M31 as long as it was clear, because I couldn't wait to see if it was changing in brightness and could I track that. And what I found was that my greatest fears came true. M31V1 was dimming and the moon was waxing toward full and moving towards Andromeda. And I became very concerned that as my chip got brighter and brighter, it would wash M31V1 out and I would lose it. And of course, then I would not be able to measure its minimum and not get an average magnitude. But M31V1 came through for me and it brightened before the moon got full, and I'm happy to report that I never lost it. And then after 57 nights of imaging, the Portland weather deteriorated. I had weeks of solid clouds, and that put an end to the project. But I was confident with 57 nights that I had at least one cycle of the Cepheid. Of course, if you image for over 2 hours a night over 57 nights, you acquire over 100 hours of luminance data. And I've never had 100 hours on a single object. And fortunately, at the end of some nights' runs, I had gathered some RGB data, so I decided I can make an image out of this region of M31. And here it is. And so this is my version of plate H335H. And I can just promise you that somewhere in here is a very faint M31V1. But like Hubble, I could not resist making red check marks and VAR, all in capitals, exclamation point, to mark its location. Now, when you have a lot of data, it's sometimes fun to compare one's results to what the Hubble Space Telescope can do. So I looked in the Hubble archive to see if we had any decent images of M31V1 besides those little thumbnails that I showed you earlier. And I found only one image, and it occupies this region. Now, this is a 35 millimeter chip, which means that the part of my chip that corresponds to this Hubble image is about 2.5 millimeters in diameter. And there's not really much in here except a little bit of dust, but I thought, let's just do a comparison and see how I did. So here's that Hubble image I found, and down here at the bottom with tick marks, you can see M31V1. That's one of the triangle stars here. And besides resolving the diffuse glow of M31V1 into countless stars, the most detail we can see really has to do with dust clouds and a few star clusters. So up here at the top, we've got a serpentine dust cloud wrapping around this bright star. Down here is a rectangular dust cloud with pointy corners and a much darker center. Here's an upside down T-shaped dust cloud. Over here, we've got an arrowhead of blue and orange stars with a dark glob beneath it. And here we have a big C-shaped dust cloud with a knob on the end and sort of a diffusely glowing red star cluster over here. Up here are the two prettiest features, two blue star clusters, and there's this little triangle of red giants in front of it. So again, this is about 2.5 millimeters on my chip. But if we look at a similar area, you can see that I actually did catch a lot of the detail of these dust clouds. Here's the serpentine cloud wrapping around that bright star. Here's the dust cloud with the pointy corner and the dark glob. Here's the upside down T-shaped cloud. Here's the arrowhead of blue and orange stars with a dark glob. And here we've got the C-shaped dust cloud with a knob on the end and the glow of that reddish star cluster. And up here are those two blue star clusters with the triangle of red giants. So again, considering that this is an infinitesimally small part of my chip, I didn't think I had done too badly against the Hubble Space Telescope. But enough romanticizing, it's time to actually do some data analysis. So I next calibrated and stacked the sub-exposures for each night into an integrated image. And then I measured M31V1's nightly magnitude on each night's integrated image. And from that, I went ahead and constructed my light curve for M31V1. So here I am measuring the magnitude of M31V1 on one of the nightly stacks. And variable star work tells you that you want to pick a comparison star that's close to your target star, both in geographic location on the chip and as close as possible in matching magnitude. So the AAVSO chart that I had told me that this star at magnitude 16.3 fit those two criteria the best. So on the calibration window, I put in magnitude 16.3, clicked extract from image, and then clicked on the star, and then my software was calibrated, and that worked really well because in the yellow circles are other comparison stars on that chart, and they all read correctly to within a few hundredths of a magnitude. So that gave me great confidence that when I read M31V1's nightly magnitude, I would get an accurate reading. So putting the bullseye over M31V1, you can see on this night, I got a reading of 18.739. I would round that down to 18.7 because I only have one decimal place in my comparison star. So going through all 57 nights, I made charts where I put observation night number in one column and the nightly magnitude reading on the other column. You can see there were some nights where I missed data due to clouds, but then I could make a light curve out of this by plotting the night number on the x-axis and the the magnitude on the y-axis. And so doing that, here is my light curve for M31V1 over the 57 nights. And the first question we have to ask is this representative of a Cepheid? And I would argue, yes, this is a very characteristic light curve for a Cepheid. So let's go ahead and extract the critical information from this light curve that we need. The maximum magnitude at both peaks came out to be 18.6. The minimum magnitude at both troughs came out to be 19.8. Therefore, I had an amplitude of 1.2 magnitudes, which is the same as Hubble got, and my average apparent magnitude, little m, came out to be 19.2. Now we want to measure the period between maxima, and it's very convincing that these two nights of observation correspond to the maxima. But I need decimal days to be as accurate as possible, and that's not easy to do from this graph. But there's an easy solution. If you go to the Fitts header of any image, it lists the Julian date of the observation down to 10 decimal places, which is literally microseconds. So getting a period with decimal values was quite easy. All I had to do was take the JD from the Fitts header of the second maximum image, subtract the JD of the first maximum image, and doing that, I got a period of 31.91 days if I rounded that off to 2 decimal points. Now that is not the same as Hubble's period of 31.415 days. That actually was not going to be possible for me because 31.415 days actually occurred during daylight hours. However, not to worry. You got to remember the Leavitt law is a logarithmic relationship. And fortunately, the logarithm of 31.91 is essentially the same as the logarithm of 31.415. They both round off to a value of 1.50. So with that, I have everything I need to calculate my distance to M31, and I'll give you a little warning, that's going to involve some complicated math, but this would be another time to ask if there are any questions about how I made my observations or acquired my data.
There was one question, Rob, but I think we've taken care of it. I'll just read the question. I
Okay.
might have missed it, but how were you sure the star in Andromeda was not just in front of it?
Well, that was a question that when Hubble sent a letter to Shapley telling him of this discovery, Shapley, of course, did not want to believe that. So he responded, he said, I'm very interested in your observation of a star in the direction of M31. And he didn't really want to concede it. But later on, he sent the calculation. So it's basically by the distance. There shouldn't be any intergalactic star of the distance that we're going to derive. And so Hubble later sent a letter to Shapley with those calculations, and Shapley held up that letter and said, this is the letter that destroyed my universe. So we'll see that when we calculate the distance.
Okay, we're all set.
All right. So if I was going to continue following in Hubble's footsteps, the first thing I wanted to do was to compare my results directly to his. And that meant that I would need to use his flawed calibration of the period luminosity relationship that gave him the wrong distance. So going back to his 1929 paper, this is the graph of figure 3 that he published in it, showing his version of the period luminosity relationship. It's different than the graphs I showed you earlier, because in this graph, he put the logarithm of the period on the vertical y-axis and the absolute magnitudes across the x-axis. Now, I spent a lot of hours of my life determining the values of all these little crosses and circles and dots and triangles, and then running a linear correlation through it to get the best fit line. But there's the best fit line. And so now we're going to take the logarithm of my period, which, as you recall, turned out to be 1.50, run it over to the best fit line, and then run it up to the absolute magnitude, where I got a reading of minus 3.6. Now, there's one trap in this paper that we have to watch out for. Hubble shifted this period luminosity relationship up about 0.6 magnitudes in brightness. He wrote that he was not very confident about his magnitude readings during the dimmer portion of the Cepheid cycle, but he was very confident about the magnitudes at maximum. So he shifted the graph to represent not the average magnitude like Leavitt had proposed, but the photographic magnitude at maximum. So I'm going to need to not use my average magnitude to go with this absolute magnitude, but use my own maximum magnitude that I derive from my light curve. So the one thing I haven't told you yet is, how do you calculate the distance once you have a matching set of absolute and apparent magnitudes? Well, the relationship between absolute and apparent magnitudes as a function of distance is described by an equation known as the distance modulus. This equation reads little m minus capital M is equal to 5 times the log of d over 10, where little m is the apparent magnitude, capital M is the absolute magnitude, and d is the distance in parsecs. Now, in this form, the equation is essentially useless to us. But if we solve this equation for the value of d using the rules of logarithms, we get d is equal to 10 to the power of little m minus big M plus 5 all over 5. And if you want the answer in the much more familiar term of light years, you simply multiply d by 3.26 light years per parsec. So I'm finally ready to calculate my distance to M31 with my own distance modulus. So here I inserted at capital M my value of absolute magnitude at maximum derived from Hubble's calibrated graph of negative 3.6. And recall here I need to insert not my average magnitude, but my photographic magnitude at maximum, which was 18.6, as you recall from my light curve here. That reduces to 10 to the power of 22.2 plus 5, all divided by 5. And I would like you to just remember this value right here of 22.2 for later. That further reduces to 10 to the power of 27.2 over 5, which ultimately reduces to 10 to the power of 5.44. So I put that into my Hewlett-Packard 25 calculator, and it spat out a distance of 275,422.8 parsecs, which if we multiply by 3.26 light years per parsec gives me a distance to M31 using my own data of 897,879 light years, which is not very far off Hubble's value of 900,000 light years. So I was thrilled. I had calculated the distance to M31, and just like Hubble, I had proved that it was so far away, it had to be another galaxy. And furthermore, using amateur equipment, I came within 2,121 light years of the correct value. But I thought, where'd that 2,121 light year error come from? So then something really remarkable occurred to me. One day I was reading Hubble's paper for the 100th time during this project. And Hubble didn't show a lot of his calculations, but the one thing he did show is that the value he got for little m minus big M came out to be 22.2. And I said, wait a minute, I know that value. That's what I got in my own distance modulus equation, 22.2. That came from my maximum magnitude of 18.6 minus my absolute magnitude of negative 3.6. It equals 22.2. And that meant only one thing. If Hubble had gotten 22.2 and run it through his Hewlett-Packard calculator, he would have had to have gotten a value of 275,422.8 parsecs, which is equal to 897,879 light years, the same numbers I got. That is dictated by mathematics, pure and simple. It then became apparent to me that those were the numbers Hubble had to have gotten, and he simply rounded those numbers off to 275,000 parsecs or 900,000 light years. And this meant that when I got a value of 22.2, just like Hubble did, I had precisely duplicated Hubble's result. So now I was basically thrilled to death. That was just astounding to me that I could do that with amateur equipment. Still, we all know that 900,000 light years is not the correct distance to M31. After Hubble published that, other people worked on the period luminosity relationship. And in the 1940s, Walter Baade found the errors in Shapley's calibration and corrected them, and he changed the distance to M31 to 2,200,000 light years. And that's the value that I grew up knowing and followed into my young adulthood. But even this distance was to change with the advent of the Hubble Space Telescope. One of the chief objectives of launching the Hubble Space Telescope was to get trigonometric parallaxes on Cepheids to come up with a calibration of the period luminosity relationship of unprecedented accuracy. This is actually measuring something called a microparallax, which can only be done from space. So the Hubble Space Telescope did that on 10 Cepheids, and if you read that paper, the Hubble Space Telescope period luminosity relationship is described by this equation, where absolute magnitude is equal to minus 2.43 plus or minus 0.12 times the log of the period minus 1.0 minus 4.05 plus or minus 0.02. So you can see there's a little bit of uncertainty in that. But it is this calibration of the period luminosity relationship that has given us our currently accepted value of the distance to M31 of 2,537,000 light years. So obviously, the real test of the accuracy of my data and the success of my project would be for me to put my data into the Hubble Space Telescope period luminosity relationship and see how close I could come to this actual distance. So if we throw out those little error amounts, we get this equation. And if I put in the logarithm of my period, 31.91 from my light curve, this time I'll spare you all the math and tell you that reduces to an absolute magnitude of minus 5.27. And so if we put that into the distance modulus equation here at capital M, This time I'm going to use my average magnitude derived from my light curve because this is a standard Leavitt calibration of the period luminosity relationship. And if you recall, that value of my median magnitude came out to be 19.2. So again, I'll spare you the math and tell you that reduces 10 to the power of 5.89. And that is a distance of 776,247.1 parsecs, which, if I multiply by 3.26 light years per parsec, yields my ultimate distance to M31 of, drumroll please, 2,531,000 light years, which is only 6,000 light years off the correct distance. So to summarize, I was able to image M31b1 with my own backyard telescope and actually measure its nightly magnitudes. And from that, I produced a Cepheid light curve. Using Shapley's calibration of the period luminosity relationship, I calculated the same distance to M31 as Hubble had, namely 900,000 light years. And now using the much more modern Hubble Space Telescope calibration of the period luminosity relationship, I derived a distance to M31 that is extremely close to the current value. These were thrilling experiences that I am going to remember for the rest of my astronomical career. But most of all, it really told me what a fabulous hobby astronomy is. Want to be an amateur archaeologist or say an amateur paleontologist? Great, I applaud you. But after you get your own pickaxes and shovels, good luck getting access to your own Egyptian tomb or your own T-Rex fossil bed with which to conduct your own research projects. I promise you, those materials will be reserved exclusively for the professionals. Not so with amateur astronomy. We amateurs have unrestricted, unlimited access to all the same materials as the professional astronomers have. And that is the entire sky above us. Think about it. I got to use the very same star that Hubble used to change the universe, and I didn't need to ask anyone's permission. And I got to use it as long as I wanted, no questions asked, and I can even use it again. And the best part is, even you can use it while I'm using it. And with access like that, the sky is literally the limit of what we amateur astronomers can do. And with that, I will stop sharing.
Awesome.
Well, Rod, you
Fantastic.
probably can't hear it, but I think there's a lot of applause going on over on YouTube, and so I'll just add my little applause.
Well,
If
thank
you wrote
you.
that up, it would be a small book. That would be 30, 40 pages worth of writing, I'm sure.
Yeah,
You're going to condense that down to 1,000 words for Sky and Tell? Or?
Allison Klessman, who's the senior editor at Astronomy, is corresponding with me about which parts we have to cut to get it into a reasonable sized article. But I'm sure she'll do it. She's very competent.
There was a question. Let me just scroll back to it. I'm not sure. Let's see. What would be the uncertainty in measurements and distance, not comparing to published data, considering magnitude, precision, period, etc. being used? And he understands that M31 is really not flat, so the distance. So
Yeah,
is this the distance to the core?
We're actually getting the distance to the Cepheid, which is in the near spiral arm. Hubble found about 40 some Cepheids with an M31, and he plotted all of them on that curve I showed you. And then he basically took a combined distance using all of them. But it's like, I was sad that I only had 1 decimal point on my comparison stars. I really would have liked to have had a little more magnitude resolution and see if I could have gotten even closer. Because that's what this is really about. It's all about the number of significant digits that you have. And so I basically could get 3 to 4 significant digits in my measurements. But when I was reading the magnitudes, they were accurate to within hundredths of a magnitude on the software.
Have you thought about going back and doing the same thing with a Cepheid that perhaps is a little easier to image?
Is a little bit what, Eric?
A little easier to image, perhaps a little more, few
I
more
think
photons.
M31V1 is about the brightest one in Andromeda Galaxy.
Wow.
If I can share, but I do have a project for next year. If I can share my screen again here. This was one of the last images I took last fall, but that is M33V3, which is a Cepheid in M33, and it's brighter than M31V1 is. So it should be easier to image, but we can impugn that because M33 and M31 are roughly the same distance. If this is a much brighter Cepheid, it's going to have a much longer period, which means I'll need to image it much longer. But that'll be a project for next year. Another place that we have amateur range Cepheids is in Barnard's Galaxy, NGC 6822. There are quite a few there, and they're a lot brighter than they are in M31 and M33.
Can I ask where your telescope is?
It's in my backyard in Portland, Oregon, in a Bortle 6 sky.
Alex, did we miss anything?
No, I think we're fine. There was a question about parallax, and once we got the magnitude correlated with the distance from parallax in the first place, we didn't need parallax anymore. And then when Hubble Space Telescope corrected the parallax readings, we had better indications of how far away things were. Is that a good summary?
Yeah, that's a pretty good summary. Statistical parallax, I mean, I can show you how that works if you want to see. I've got a little demonstration of that.
So what kind of angle does Hubble have? I mean, it can't have much.
It's micro arc seconds. If it images 6 months apart, but that's essentially what Gaia and all these other parallax telescopes that give us all the light year distances in the sky and things have been derived from. They're actually very good at measuring micro parallaxes, but Hubble's the best because it's got the biggest mirror.
Did the question get asked about how are the magnitudes that the comparison stars for this star, how are those determined for her Hubble back in the day?
Oh, that was done by, it was a long daisy chain of measuring the diameter of stars on what were known as seed 30 photographic plates, which those were very well characterized. And so they had a whole table of how big the dot would be for a particular magnitude that was compared to other work that they had done at the Harvard College Observatory with photometry. And so, yeah, it was a long daisy chain of events to get those magnitudes. And so they had to make compensations. If the star was 6 millimeters in diameter, but it was a 45-minute exposure, that wouldn't be the same as a 6 millimeter star in a 1.5 hour exposure.
So were they guiding, or was that telescope tracking well enough?
Hubble guided. Those pictures I showed you were of Hubble guiding, but they didn't move the telescope. They moved the plate. They kept their little galaxy on a crosshair, and they actually had to move the photographic plate to keep it in registration because you couldn't guide that telescope. And of course, the photographic plates were so slow, it didn't result in trailing when they did that.
And okay, yeah, I think we got that one. Barbara Harris wants to know why not use the photometry module in Maxim DL to get a more robust measurement of the magnitude. You were using Maxim DL, right?
I was using Maxim DL. I was using the photometry tool, and Barbara was one of the authors of that paper, by the way, that I showed. She's the senior author on that paper, and so we owe a great debt of her in doing that work. But I did them all by hand. Before I took a magnitude reading, you could just put all the files in a thing and it would run it and would give you a light curve. But I did not get as accurate results. And so I basically calibrated, and then I checked every other comparison star on the plate. And when they all read the best, that's when I would actually go read M31V1. And that was I thought I got a very tight light curve. A lot of light curves look sloppier than that.
Do you feel a little remorse of not doing a lot of imaging during this process?
Only a bit. I really wanted to do this project for years. So this is my second astronomical distance project. During the transit of Venus, I went to the summit of Haleakala in Maui, while a colleague of mine stayed back here in West Richland, Washington. And we took simultaneous images of the transit of Venus and calculated the parallax, and we got the distance to Venus and the sun within 3% of the correct answer, which was the width of 1 pixel on our DSLRs. So although it's a bigger error than I had for this, it's down to the pixel, and I can't do much better than that. And that was published in the 2013 issue of Sky and Telescope.
You just need smaller pixels than the 9 micron pixels you have with the 11,000.
That was a Canon 20D, which had like 6.4 micron pixels. That's all I took to Maui.
Yeah, I was on Mount Wilson that day. So
historic place to be.
Yeah, that's where all this happened. I've looked through that 100-inch telescope that you were talking
I envy you for that. I would love to do that. I need to go there. I made a pilgrimage to it, but I couldn't go in. And I did pick up a rock from the base of the dome, and that rock is under my dome. And I thought about that little rock a lot while I was out there shooting this. I thought, this is the second time a rock has been near a telescope measuring the distance to M31.
Oh, you look like you're working on M33 now. And what other projects do you have where you're going to try to replicate this?
Just M33, maybe Barnard's Galaxy. And then I have another Hubble project that I'm not going to disclose so I don't get scooped.
Oh, okay. But you can tell me.
Okay. During the after show, Alex.
You know, I'm not sure that anyone on this call, or I don't know about anyone on YouTube, would really have the patience and the expertise to do what you did. I was thinking about it and I was going, no, I couldn't do that.
You could. I hope somebody else does it. I mean, it's pretty thrilling to measure the distance to another galaxy and get it. I mean, when I started out, I thought, I don't have to get the right answer. I don't even have to get what Hubble get. I just need to get a number that proves it's outside the Milky Way. That's all Hubble did, and I would have been happy with that. So to get as good of an answer as I did was really quite thrilling.
I might have missed it. How much integration time did you do for a given observation?
They were typically 2 hours. I mean, I went as long as I could every night, but they typically.
I guess the period is long enough that you can stack quite a few images.
Yeah, that did not matter.
Okay.
You know, I come from the Northwest, actually Washington, and I can't imagine there's enough clear nights where you are.
Well, it's not just that. It's also wildfire season. And I thought if we had another wildfire season like we'd had the year before, this would come to a crashing halt.
Well, I can tell by your enthusiasm, your sense of satisfaction, the challenges, and just the way you were excited about what you did. It was really a heck of an achievement to get all that stuff done. And I could just tell the people on watching tonight have really been inspired by it. Okay. And if maybe they aren't going to pick up that particular astronomical challenge, but they'll pick up some other one. And that's kind of one of the things we do on the Astroimaging channel is kind of try to inspire people to pick up their game in astroimaging and stuff like that. So that sure was a great presentation for us. Thank you.
Well, thank you very much. It was a pleasure making it, and thanks for watching.
When the program's over, you want to hang a little bit with us?
You bet. That's always fun to hang with you guys. So
yeah. Okay. So that's, I guess, about it for the night, right? We got all the questions answered, and we still got our audience out there. I hate to have to go, but we got to go sometime because there's another week coming up next week, and we'll be back here again next week and learning more about astroimaging. So, Tim, I think you're in charge tonight. Take us out, dude. Bye.